So the purpose of today's lab is that we want to see the relationship between force, mass, and acceleration. Okay? Basically, we want to confirm Newton's second law. We want to see if truly net force is the vector sum of all forces and mass times acceleration. We just want to very simply confirm that relationship. All right? So that's what we're going to do. We're going to do it using an apparatus like this. Okay? The setup for the lab will be as follows. Okay? You're going to have one of those carts that talks to your phone, okay, and gives data, and it's going to be on the track, and it's going to be connected over a pulley to a hanging mass. All right? That hanging mass is going to change throughout the lab. All right? By changing that hanging mass, what am I changing for this system? Well, the acceleration will change as a result of me changing the hanging mass, right? The more mass I put over, the faster the system should accelerate, okay? What am I changing when I change the hanging mass?
Force.
Exactly. I'm changing the force in this lab. I'm changing the applied force, which, if everything goes perfectly to plan, should also be the, okay, yes, it will be the force of gravity. It will be the, what kind of force? Yeah, it should be. If everything goes perfectly, it should also be the net force. Now, is everything going to go perfectly?
No.
Okay, what's probably going to throw a monkey wrench into this?
Friction.
Friction. Yeah, there's going to be a little bit of that. Not a lot, a little. Okay? There could also be some other issues involved with the setup of the lab. For example, we've been talking the last couple of days about these things. Do they change some forces?
Yep.
Okay, I'm going to do my best to make sure this is not one of these. Am I going to be 100% sure I don't? Nope. Will I be able to tell? Actually, I will.
Do you have a level?
No. Well, yes, you do. You can use your phone. Okay? Okay, what's that? Yes, the level app is still on the phone. I used it just the other weekend to level my trailer around the camp.
Nice.
So the level app is still in there. So if you have an iPhone, it's
The compass?
it's in the compass one. Yep. Okay, so if you go into compass, okay, and then, sorry, not compass, no. Not compass.
Isn't it measure?
It's measure. Yeah, you have to go into measure. Okay, so go into measure, okay, looks like a ruler, all right, and instead of measure, click on level, okay? You can put your phone down on top of there and it'll tell you whether it's level or not, okay? And it'll even tell you which way it's out. So right now it's tilted that way, oh, and now that way. See how the circles move, okay? When I have it perfectly level, well, you can't see it now because it's level, okay? It should just read 0 and it'll turn green. Okay? Now you got to do your best. It's probably not going to be perfect, okay? But you do your best because you're going to be setting this on your desk. Now, your desk, you should, well, two desks actually, you should be able to get them pretty close to level side to side. But your desk's also what? It's also tilted a little bit, so you got to take that into account too. Okay? So there's going to be a little bit of leveling involved. Okay? When I'm done this lab and I start looking at the acceleration of the cart, okay, because that's part of our analysis, okay, I can calculate the net force. In theory, that net force should be equal to the force of gravity acting on the hanging mass. That's what it should equal. Okay? But there's two situations that can come up. Okay? The two situations are that force, that net force is bigger than the force of gravity, or that force is smaller than the force of gravity. Okay? Those are the two situations that are going to come up. You're not going to get it to be perfectly equal. It just never works that way. Okay? So one of two situations will come up. What you have to do in the analysis is basically look at your results and tell me, okay, which situation am I in, and what does that mean? What forces were involved to create that situation? Why was my net force actually bigger than the force pulling forwards? Or why was my net force smaller than the force pulling forwards? And talk to me about, in your analysis, what other forces were involved and what direction were they pulling. Okay? There's a fair amount of thinking involved, okay, in that part of the analysis. Everybody with me on that?
Are you recording?
I thought I was recording. See? I am.
Oh, okay.
Okay, good. All right. back to our background here. That's the back. We just went over all the background. Okay, so the problem we're investigating, we've already talked about. What's the relationship between force applied to an object and its acceleration? Well, hopefully it's linear. Okay, hopefully that when I increase the applied force, the acceleration will increase. Okay, all right. So in the design here, okay, this experiment involves these variables: the applied force that we're using gravity to get. Okay, the acceleration, the cart's mass, and the system's mass. Okay? Now, if we remember anything about systems, okay, it's that all parts of the system must accelerate at the same rate. Okay? Now, if I change the mass of the system, will I change the acceleration? Yes. Do I want that? No. Okay? If I change the mass of the system, that's one other thing that can affect acceleration. The only thing I want affecting acceleration is the force. Okay? That's the only thing. That's what I'm changing in this lab. We just said that, right? It might be our manipulation. Okay? It's that thing that we're changing. We want to know what's the effect of that on the acceleration of the cart. If I change anything else, my experiment is meaningless. Agreed? I then have two manipulated variables, and I don't know which one causes the change. All right? So I need to make sure that the mass of my system stays the same, but I have to change the hanging mass. How am I going to do that? The answer is I'm going to read the procedure and follow it carefully.
Yay.
Yay. Okay? So what we'll do is we'll start out with a small amount of mass hanging over the pulley and some mass sitting on the cart. Okay? And then what we'll do is we'll move mass from the cart to the pulley. That keeps the mass of the system the same, but allows me to change my applied force. Everybody follow? Okay? Because the mass of the system is always the combined mass of the hanging mass and this object over here. As long as I move the mass within the system and don't take it in or add any more, okay, then I should be good. Everyone all right with that? I might be talking about a certain kind of variable there, the kind that stays the same. Okay. All right, our hypothesis. Okay, the if part of our hypothesis needs to talk about Newton's second law. What does it say? Basically, in the if part of the hypothesis, you should be kind of talking about what Newton's first law is. Sorry, not Newton's second law. Did I say first law? Yeah. I feel like I said first law. Second law. Okay? So if Newton's second law says the following, or if Newton's second law is this, okay? That's what we need to talk about in the if part. Okay? The and part describes the experiment. Okay? In this experiment, the applied force is being changed, the acceleration is being measured, okay, something like that, and describe that. Okay? The then part, okay, needs to talk about what's going to happen in this lab. All right? So in particular, what's going to happen to the acceleration of the system as you change the applied force. Okay? Okay, on the sheet that you have, well, the electronic sheet that you have, it says that the mass of the cart is 502 grams. Those were our old carts, okay? Mr. Dickey measured the mass of the new carts. Oddly enough, the blue carts are slightly heavier than the red carts, but there's a piece of tape on the cart that tells you their mass. Okay, so you'll need that. For the blue carts, they're both 270, and I think the red carts were lighter. I don't know why. They should be identical, but maybe red plastic is less dense or more dense than blue plastic.
And then paint is the heaviest kind of paint. So
well, it's not really painted. It's like molded plastic, so I don't know. But they were different. I watched him do it. Okay, it wasn't just that he screwed up. Okay? He did it right, but it was weird. Okay, so like I say, the masses are written on a piece of tape on the carts. Sorry, the red carts are heavier. They're 274. 4 grams difference. I don't know what, but they are. Okay, that's a number you need. Now you're going to be putting masses on the carts, like we said, right? You're going to have some masses on the cart. You're going to have some masses hanging over the cart. Those masses are prescribed in the procedure. So you need to follow that carefully. We do not want to put too much mass over the pulley. If we do, the cart will accelerate so quickly that we won't get good data, and we're likely to break them, right? Because they could fly off the ramp or hit the pulley and break the pulley, okay, and then break the cart, and then bad things will happen after that. Okay, so we don't want to go there. We have to be kind of careful about what we're doing. Now, in order to keep the masses on the carts, every group is going to need a little bit of fun tack. Okay? Because if I just set the masses on here and then let the system go, Newton's first law will take effect. The cart will slide out from underneath the masses sitting on it, just like a magician pulling the tablecloth out from under the dishes. We don't want that. So you're going to put just a tiny little bit, and by a tiny little bit, I mean like, okay, a little more than that, about that much on the bottom of the mass. Okay, or stick it on the cart and push the mass into it. Okay, that'll be enough to hold it in place. You don't need this whole big lump. Okay, just a little. Right, so that'll be on the table as well. Take a little bit of that. Okay, so in step 1, okay, so we're not going to be using the motion sensor or the force sensor anymore because now we have the cart that has it all inside anyway. Okay, so all we're going to be doing is writing in our table here, okay, our different masses, and then calculating a few things here. So we're going to, you got a table like that. I think I put it in your report, did I not? Okay, so what we'll be doing is, okay, in trial 1, okay, we're going to have the mass of the cart, which isn't 502 anymore, okay, plus some masses. So in that first one, whoops. Thought I had it in the procedure. Oh, I don't. Is it on yours? Did I put the masses in your procedure? I didn't. Okay. Well, we're going to go with the ones I have on this chart. Okay, so in the first one, you're going to have 50 grams hanging over the pulley. Okay, so that's 0.05 kilograms, 50 grams hanging over the pulley. Okay, and you're going to have 270, so you're going to put 400 grams on the cart. Okay, so we're going to have our cart plus, okay, 400. So we'll have cart plus 400 grams. Okay, everybody with me there? That'll be trial 1. 50 grams hanging, okay, and cart plus 400 grams. Actually, I'll write kilograms because that's what it should be, 0.4 kilograms. In trial 2, I'm going to move 50 grams off the cart and put it over the pulley. Okay, so now I'll have less mass. I'll have the cart plus 0.350 kilograms, and I'll have 100 grams over the pulley. Okay, so each time we do this, we're taking 50 grams off the cart and moving it over the pulley. Okay, we're going to do 4 trials. Okay. Each time we move 50 grams off the cart and over the pulley. Everybody clear on that? Okay, you're going to want to set your data collection rate pretty high. Okay, the default seems to be like 10 hertz. Okay, you need to check the sample rate when you're in Sparky. Okay, set it really high. It can set, I think it can go as high as 200 hertz. Okay, I'd say like 50 hertz to 100 hertz is probably good, right? Because this lab, like the amount of time it takes the cart to accelerate is not very much, right? We want to get some good data points, so set the sample rate to probably at 50 hertz. Okay, then we'll get probably 20 points, something like that. Everyone okay with that? Okay, so those are your 4 trials. Okay, those numbers you'll need in there. So in this one here, okay, cart plus 0.300 kilograms. Okay, cart plus 0.250 kilograms. Okay. All right. The applied force is just the mass times what? Right, hanging mass times gravity, that'll get us our applied force. You can calculate that really easily. Okay, the acceleration you're going to get from Google Sheets. Okay, because once you have your data, you're going to take the velocity versus time data and make a velocity versus time graph. The slope of that line for each trial is the acceleration of the cart. We learned that in Unit 1. Okay, so you just need to get a line for each trial, get its slope. Okay, put that in here. All right, then calculate the net force. Take the mass of the system times the acceleration. Okay, now we said that theoretically this number and this number should be
Equal.
right. Are they going to be? No. They'll be close. Okay, they'll be close. Everyone okay with what we're doing there? Okay, so a lot of that is parts of your analysis there. Okay. Oh, there it was. Here's the other one. Here's the rest of the procedure. Okay. All right, so you're going to end up with a graph, right, where we're going to see the acceleration increasing as we obviously put more mass over the pulley. Okay, so it looks something like that. Okay, then you've got these analysis questions. So the first one is just about your graph, building your graph. Okay, calculate the applied force, filling in your chart. Okay, calculate the force on the carts. Okay, that's in your chart. What's the relationship between net force and acceleration? All right, so when you see this, okay, you're looking at your net force and your accelerations. If one goes up, what does the other do? That's what you need to write down. Okay, number 5, this is where you need to look at your data. Draw a free body diagram describing the forces involved. So that's what I was talking about before when I said, if you have a net force that's bigger than gravity, what does that mean? Okay, if you have a net force that's smaller than gravity, what does that mean? This is where you show me that. Okay, you draw a free body diagram that includes whatever other forces you think might be involved to create that situation. Okay, number 6, you explain it. Okay, so 5, you diagram it. 6, you explain it. Okay, then you got your conclusion. Same as always, copy and paste your hypothesis. Explain whether your data supports or refutes sources of error. All right, questions? Okay, so make sure somebody in your group has the SparkView app. There should be enough tracks, okay, for the 8 carts. No, I need one more track. Okay, but they'll all work. Even those white ones will work. When you set this up, you need to be careful. One person's job has to be to stop the cart. Okay, one person needs to catch the cart before it hits this pulley. If it hits this pulley, it'll break the pulley, and the cart will jump the pulley and smash into the ground. We can't do this one on the ground. If you're looking at me wondering why, really think hard. Okay? So these pulleys are really good. We don't want them to get broken. Okay? They're like nearly frictionless. They spin for a really, really, really long time. Okay? So we want to preserve them as well as these very expensive brand new carts. Okay? So one person's job is just to stop the cart when it gets here. Okay? All right. You're going to need a piece of string. I found the hardest part of setting this up was getting the string to go through this hole. Okay? I had to push it through with a paper clip. You might be able to do it with a pencil or something. Okay? Push it through, tie it on, okay? And then make sure your string is long enough so that, okay, when you hold when the masses are hanging here, they've got room to drop. Okay? I have people who like cut a whole length of string, so they start out like this and the masses are already on the floor. Lab doesn't work very good that way. Okay? Now, this thing is only going to accelerate until the masses hit the floor. Okay? Then it's over. All right? So just consider that when you're looking at your data. You'll know when that happens. Okay? Because the graph will change. Okay. Grab the stuff you need, and let's get started. If you need help, I'll come around and help you.
I use yours as a footer.
Our boys. Sitting Grace down and stuff. That's like
in your bonding is acceleration and the control is
When I change the mass, I change the I'm always changing the mass, change the Okay, the confusion I'm hearing here is what the manipulated variable is. Guys, the manipulated variable is not mass. Okay? Mass is not being manipulated here. I'm changing where the mass goes so I can change something else. What's driving the system? Okay, gravity's acting as an applied force.